It's my pleasure to introduce a distinguished alumna of the University of Western Ontario as an undergraduate. Now just down the road at the University of Waterloo. Doreen is going to talk more about quantum.
Thanks, Wayne. So I guess the first thing I should do is explain the strange title of my talk, which has the part 2 at the end. So what I'm going to be presenting today is one thread of a longer paper. And of course, what I'm going to be focusing on is all the respects in which I disagree with everything that David has just said. So if you want to see part 1 of this talk, I have more to say about other issues. I'm going to try not to get sidetracked by the other issues today. If you want to see part 1 of this talk, you have to come to Washington, D.C. next week to the New Directions and Formulations of Physics conference where I'm going to be doing the rest of the story. All right. So I want to start out by pointing out that although David and I are going to get quite specific about different pieces of evidence in favor of our different points of view, that actually what we're talking about is a really fundamental conflict between intuitions that I think not only philosophers of physics have, but philosophers of science have about the sort of thing that we should be doing when we're doing philosophy of science. And in particular, I think this sort of thing comes up fairly often in philosophy of physics. Okay, so here's what I take to be a representative quotation from somebody on one side of the debate, Paul Teller, who eventually, in his book, on page 146, gets to explaining why it is that he, in his book on field theory, he deals with the Lagrangian approach, with cutoffs, instead of using an axiomatic approach. He says, formal and rigorous work in axiomatic field theory is not discussed because although axiomatic field theory is a useful enterprise in studying the formal properties of quantum field theories, axiomatic quantum field theory as it exists today does not appear usefully to describe real physical phenomena. So you've heard me saying something along these lines. So this is the one intuition that we often have as philosophers of physics is that what we should be doing is we should be looking at the theories that physicists actually apply. And furthermore, we should be looking at the context of application of those theories, even if it gets a bit messy sometimes. And even if things aren't as cleanly formulated as we would like, there seems to be an intuition that we should be dealing with the real physics. Here's the intuition on the other side. A quote from Hans Halvorsen, who admits that the algebraic approach is indeed idiosyncratic in the sense of demographics, but he says, there remains an implicit working assumption among many philosophers that studying the foundations of a theory requires that the theory have a mathematical description. And moreover, whether or not having a mathematical description is mandatory, having such a description greatly facilitates our ability to draw inferences securely and efficiently. Okay, so what he then does, his co-authors then to go on and securely and efficiently draw a great deal of inferences from the algebraic framework having to do with different aspects of quantum field theory and its implementation. So this is the other intuition, that actually we'd like to make progress as philosophers of physics. We have this interpretive project before us, and one way of making progress with both the interpretive project and the project of understanding the conceptual foundations of theories is to look at formulations of theories that are mathematically more rigorous, really axiomatized in the two, but at least mathematically rigorous and consistent. All right, so these are the conflicting intuitions that I play here. What I aim to do today is I accept, I take Paul Teller's point. I think that that's not relevant in the case of quantum field theory, and I'll explain why. I also take Hans's point. But I think that we can do a little bit better than this in the case of quantum field theory. That we can give, I'm going to give different arguments for, additional arguments for why we should be interested in looking at the axiomatic approach. One example of which is the algebraic approach. Okay, so overview, thesis. Of course, I'm going to be arguing that the variant of quantum field theory that should be subject to interpretation, that philosophers of physics should be concerned with is a rigorous axiomatic variant. So it'll become important later why I'm doing exactly those terms. But for present purposes, the leading candidate for the axiomatic variant is the the algebraic formulation of quantum field theory. Okay, so the structure of the paper is going to be as follows. First of all, I'm going to start out by giving a clear categorization of the different variants of quantum field theory. Of course, I'm going to give an argument in favor of the axiomatic variant. And then I'm going to take out some responses to objections, which I'm not going to attribute to David. But I think some of these could be found in the vicinity of the things that he was saying a few minutes ago. Okay, so I'm not going to start with a fable. This is actually history. It's not a fable. It's history. And I think that I don't want David to get too worried because I'm just going to start out this way. But I take it that the value of starting out this way with these limitations is going to be that history has something to tell us in this case about the conceptual foundations of quantum field theory. And this is another case in which, as we so often find in philosophy of physics, toy models turn out to also give us to reveal insights into what's going on in our theories. Okay, so I'm asking you to bear with me for a moment. Until further notice, I want you to imagine that the year is 1970. So I picked that year because that's the year in which the set of papers was published by Doreen Fraser, in which they demonstrated that it's possible to construct a model for an interacting 5-4-2 system. So that's a system with a 5-4-2 interaction in 2 space-time dimensions. Okay, so that's why I picked that year. Why I picked 2 space-time dimensions is because that's the first non-trivial interacting system that was actually, that the model for axiomatization was actually constructed. So this means that we're thinking back before any of that renormalization group stuff. We're thinking back before QCD. We're thinking back before the standard model and any of those sorts of innovations. If you want to have a more concrete handle on what I'm talking about, you can think about Schwaber's introductory textbook on quantum field theory, published in 1961, which will give you a handle on some of the variants that I'm going to be talking about. I want to be clear, though, that eventually I'm going to remove these limitations. I take myself to be giving an argument which is valid in 2009 in a world in which space-time actually does have limitations. Very big limitations. Okay, so as I see it, quantum field theory, by which I mean relativistic quantum field theory, can be broken down into 3 categories. So I take it that these are variant formulations of the theory. I'm going to get to why I think about things that way in a moment. And it'll become clear in a moment why these are categories of variants rather than particular variants. Okay, so for the sake of concreteness, let's think about this Hamiltonian. This is the 5-4-2 Hamiltonian, so X there is one dimension. And we're going to think about what happens when, say, you're reading the beginning of Schwaber's textbook. You start off in the interaction picture, no renormalization or anything like that's been introduced. You're assuming that, you have that time in there, you're assuming that at T0, you can take this Hamiltonian and you can operate, you can treat this Hamiltonian as being an operator on the Fox-based representation for the free system that's represented by that HF. All right, so everything gets nicely set up. There's a whole bunch more assumptions, but for our purposes, that's the important one. Of course, what you find when you try and do this is that when you try and apply the Hamiltonian to the vacuum, that's the free vacuum in the Fox space, then you get infinity. Lots of problems with this. In particular, there's a practical problem, right? Because you're going, when you calculate the scatter scattering matrix elements, which are the sort of things you're going to be calculating in order to predict the results of scattering experiments. You're going to have, in the perturbation series, you're going to have these infinities dropping up, and so you're not going to get sensible calculations. Okay, so you're going to have to do something. There are different options. The first option is going to be to introduce renormalization counterterms. Okay, so in this case, the nice sensible thing about this case is that you only have to introduce one renormalization counterterm. That's the vacuum self-energy counterterm not there. So once you do that, then you can set it so that you get rid of the infinity, you absorb it into the Hamiltonian, you have a renormalized Hamiltonian. Okay, so clearly this way of going involves, because you have to start with, you're going to have to introduce that infinite renormalization counterterm. Of course, in general, you're going to need to introduce more than that one renormalization counterterm. Second way of going is to introduce what I'm going to call the cutoff variant. And this bears some resemblance to what David was talking about. Well, we'll see there's something we can be careful about. Okay, so in this case, it turns out, again, because we picked a particularly simple case, that in this case, you only need to introduce a volume cutoff. You only need to introduce a long distance cutoff. So here's one way of doing it. Introduce that cutoff term into the Hamiltonian. Then you still have to renormalize, but all your renormalizations come up on it. Of course, in general, you're going to need to introduce a short distance cutoff as well. And this is the case that David was necessary. Finally, the third category of variance of QFT, and this is where we genuinely get into categories of variance rather than a particular variant, is what I'm going to call trying to pick some sort of neutral terminology which doesn't suggest the wrong things to the right people, is the formal variant. Okay, so instead of trying to renormalize in different ways, what you can do is you can just try to start from scratch, right? You can interpret what's going on up here. If you apply the Hamiltonian to the free vacuum, infinity, well, that obviously means that your Hamiltonian is not defined on that state. Furthermore, if you look into it, you can show that the Hamiltonian has a trivial domain in interacting Hamiltonian has a trivial domain in that Fock space. So what you do then is you can try to find a unitarily equivalent representation of the canonical commutation relations on which your Hamiltonian in the interaction has a non-trivial domain. Okay, so I should say this is only the beginning. There are different ways of pursuing this strategy, one of which is the algebraic formulation of quantum field theory, one of which is the Whiteman axioms for quantum field theory. There are other candidates. This is just the starting point. The different axiomatizations are going to disagree about what else you have to do in addition to this. Okay. So this gives us a categorization of different variants of quantum field theory. What I would like, though, is not just a categorization, but some sort of deeper understanding of what's going on here. And what provides this, I think, is a result, going back to 1955, by Rudolf Hagg. So I'm not going to enter into the details of this at this point, but here's what's important about Hagg's theorem for my purposes. So Hagg's theorem takes as premises a set of assumptions that are built into the interaction picture in a standard textbook approach to quantum field theory before you get to renormalization. Right? All these physically well-motivated assumptions are introduced. And what Hagg's theorem shows is that if you take a certain set of physically well-motivated assumptions, then you can show that within that framework you can't represent an interacting system. Okay. So no wonder we found that when we tried to represent our simple interacting Hamiltonian in this way. Okay, so this is interesting to me because it shows that what's gone wrong here is if we take the standard assumption that what we're trying to do is represent the interacting system, then you have a straightforward inconsistency, right? that particular set of theoretical assumptions that we started off with is inconsistent with the further assumption that we're genuinely representing an interactive system. Okay, so this is nice because it gives us a starting point for further foundational work in quantum field theory. We started out with this physically quite reasonable set of assumptions. We find out that there's something wrong there if we're going to demand consistency. Okay. So before getting to the next moral about what's going on here, I need to be more precise about what I mean by quantum field theory. So I'm going to introduce this definition. As far as I'm concerned, quantum field theory is the theory that best unifies quantum theory and special theory of relativity. Okay, so a number of points about how I intend this definition to be interpreted. First of all, if you're bothered with the word field in quantum field theory, then you can substitute relativistic quantum theory for what I have as quantum field theory. So as we've been discussing, I take it that S-matrix theory, some sort of relativistic particle, quantum mechanics, are not going to be the best ways of unifying quantum theory and special theory of relativity, but if you want a larger framework in which you admit those, that's perfectly fine. Furthermore, I'm using the term quantum field theory, I guess to be more precise, I should be talking about relativistic quantum field theories. Of course, there are, as John was discussing this morning, there are non-relativistic examples of quantum field theories. I'm excluding those from present considerations. Okay, so historically we're in an interesting position with quantum field theory because it is this sort of unification project, which physicists were clear on, certainly by the time, by this, of course, special relativity in 1905, certainly physicists were clear on the fact that there was a unification project that needed to be looked into at the point at which they got non-relativistic quantum mechanics. But actually, even before that, people were trying, before they got non-relativistic quantum mechanics satisfactorily formulated, they were trying to get a relativistic version of the theory. Okay, so it's clear to us that we have this unification project. We have two theories that we think should go together. The other thing to point out is, of course, that I realize that the real world is not going to be satisfactorily described by quantum field theory. Of course, we know, as I've set things up, quantum field theory is only giving us quantum theory plus the special theory of relativity. We know that there's also the general theory of relativity, there's gravitation that needs to be taken into account. So I want to be clear, though, that in the next few minutes, what I'm going to be talking about is a particular interpretive project, which differs a little bit from the type of project David was talking about a few minutes ago. I'm going to get back to David's project, but for the moment, I'm going to stick to my own interpretive project. So the thing I care about is this question. I know that quantum field theory, as a matter of fact, can't be true, but if it were true, what would reality be like? Okay. If I have this theory, quantum field theory, and I'm interpreting it, what is my interpretation going to say that reality is like? Okay, so this is a counterfactual interpretive project, but as I will go on to continue argue for, I think it's exactly the sort of thing we need to be doing in order to get to the real world type cases. All right. So I take it that I should say something else. So of course, the reason why I set things up this way is that I take it that three variants of quantum field theory are each going to be rival theories in this sense. So they're rival theories on the same domain. They're all trying to unify the special theory of relativity and quantum theory. So they're theories about the same domain, and they're different theories. So they're rival theories. All right. So I take it that one thing that's interesting about this case, at least as I see it, 1970 and two spacetime dimensions, is that the three variants are empirically indistinguishable, by which I mean that the sets of scattering matrix elements generated by the three variants can be brought into arbitrarily close agreement. Okay, so if you take small enough cutoffs, sort of large enough cutoffs in this case, then you're going to be able to, degree of margin for error, you're going to be able to get sets of scattering matrix elements that agree. The other point to note there is that you don't actually need to use the perturbation fleet series in the constructed model, so that's another respect in which they'll disagree, but of course we're not worried about that. Okay, so that's the first part of this underdetermination claim. The second part is that at least the cutoff and the formal variants of quantum field theory disagree on matters of ontology. All right, so I take it, this is interesting, so I'm going to explain it, but I take it, I'm not going to belabor the point, because I take it that this is the point on which David and I disagree. Is that or sorry, David and I agree. Is that correct? Correct, David. Yeah. Okay. So that's not interesting if David and I agree about this. So I'm not going to talk about this too much, but I think it's worth noting here that here we have a genuine case of a advanced, complicated physical theory in which we have empirically indistinguishable theories which disagree on matters of ontology. So just to go on a little bit, here are the references. So the cutoff variant of quantum field theory has a finite number of degrees of freedom, and this is going to allow you to, even in the case of interactions, get a quantum interpretation of the theory. I won't go into details. Whereas I argue that in the formal variant, you can't, in the case of interacting systems, you can't have a quantum interpretation of the theory. And Baker has more interesting things to say about the case of field interpretations as well. Okay, so we have this sort of interesting case of underdetermination of theory by, in this case, as long as you think that the S matrix elements exhaust what there is as far as the empirical consequences of the theory are concerned, then we have a case of underdetermination of theory, of ontology, by all possible empirical tests. But as I said, I don't want to belabor that point because I think that there's a more important point at issue in this case. And there's a more important point at issue when we're trying to answer this question of, as philosophers of physics, which variant of quantum field theory should we be interested in for our projects? I think the more important point is actually, it's not just a matter of metaphysics, it's not just a matter of interpretation, but these three variants of the theory also disagree on the physical content of quantum field theory. Right? So there's a matter of physics at stake here, in addition to the interpretive questions. Okay, so once again, here's a nice way of seeing how the different variants of quantum field theory differ from each other on matters of physical content. So when I'm talking about the physical content of the theory, what I'm interested in is theoretical principles which are embraced by the theory. And this is the point on which the cutoff variant of the theory and the formal variant of the theory disagree, as well as the normalized variant, but that's, again, not something that is an issue of things. Okay, so Hagg's theorem tells us that this seemingly reasonable set of physical assumptions for quantum field theory can't all be true if we're interested in representing interacting systems. So the three variants of the theory disagree in how to modify these assumptions in the light of this reductio, in the light of this Doppler result. So first of all, you have the infinitely renormalized variant, which introduces the infinite renormalization counter terms. I'm not going to say too much about that because, as I just said, it's not. David and I both agree that this is not the variant of the theory that should be embraced by philosophers of physics. that is it's quite difficult to sort out what the theoretical principles of theory actually are after you introduce these infinite renormalization counterterms, because the mathematics of the situation is so unclear that you're no longer sure exactly what your principles are. There's different ways in which you could choose to carve up the sets of theoretical principles. So it's unclear what you're talking about there. So how does the cutoff variant respond to Hagg's theorem? Well, first of all, by introducing, in the general case, cutoffs, spatial cutoffs, at short distances and long distances. So introducing the assumption that space is not continuous and infinite. But furthermore, you're going to, the cutoff variant proceeds by rejecting other assumptions of physical assumptions as well. One of which is that, as we've been discussing, the cutoff field is not going to be covariant under spatial translations, under covariant translations generally. The second thing that's given up in this case is that the vacuum state is not unique. Essentially because you're in the context of an infinite number of, a finite number of degrees of freedom, so you lose the result that your vacuum state is unique, which might have some consequences for spontaneous symmetry greater than All right. Then what does the formal variant do? Well, the formal variant disagrees with the cutoff variant in terms of physical content because the formal variant, the approach is to hang on to these principles that are given out by the cutoff variant and to reject another principle of Hagg's theorem. So at a minimum, any axiomatic approach to quantum field theory is going to drop the principle that there's some time in which the free and interactive fields are related by unitary transformation. Okay, so to put it another way, the strategy is going to be, if you're looking for a Hilbert space representation for your interacting system, to look for one which is unitarily equivalent to the Fock space representation for the free system. Okay, so now that I've set things up the way I want them to be set up, I can explain to you why I take the formal variant to be the variant that philosophers of physics should be interested in. So at this point, I'm going to entirely ignore the infinitely renormalized variant and focus on what's at stake in choosing between the formal variant, and the cutoff variant that David is interested in. Well, first of all, in virtue of the way that the axiomatic program proceeds, one virtue of the formal variant is going to be consistency. This is not so much an issue between David and I, but it's important to note that one of the things that we get in this case from trying to get a mathematically rigorous framework for axiomatic framework for theory, and one of the things you get from trying to construct models is you get consistency, mathematical consistency. The second point in favor of the formal variant is that it provides what I take to be a principled response to the reductions posed by Hagg's theorem. The problem is we have this set of seemingly physically reasonable principles. We're going to have to reject at least one of them. How do we decide? Well, the principle that gets rejected by the formal variant, the principle that there's a time at which the free and interactive fields are related by unitary transformation, is first of all something that's mathematically suspect, because we know that in the presence of an infinite number of degrees of freedom, there are unitary representations of the computation relations. And second of all, it doesn't seem to be physically well motivated at all, especially when you compare it to the other sorts of things that you could be deciding to give up, like whether space is continuous and infinite, like whether we should make our fields be covariant under Poincare transformations, those sorts of things. All right. So, and I maintain it's not ad hoc, which will be illustrated by comparing to what I think happens when we consider that ad hoc variant. All right, so as I said, I'm willing to grant that consistency is not the point of issue here. Once you introduce cutoffs, generically you're going to be in a situation in which you have a finite number of degrees of freedom. And you still have to renormalize, but the renormalizations are going to be finite. So then we have to think about how the cutoff variant looks as a response to the reductio posed by Hogg's theory. So we have to see how it stacks up as a way of coming to terms with the fact that this set of physically reasonable assumptions cannot all be maintained at the same time. All right, so in this project, it's important to note that we have to be fairly realistic in our attitude towards the cutoffs, because the cutoffs are essential. You can't take them to infinity or 0, because then you're going to be back into the situation where you're not actually providing a certain response to the problem. So we have to regard the cutoffs as essential elements of the theory, as opposed to dispensable add-ons to facilitate calculations. So I have a but here, of course. So all of this, I take, is not problematic. Here's the problematic part. So as a response to this reductio the response to the problem of picking which of this set of physical principles that we can get rid of, the introduction of this assumption that space is discrete or finite or pactified, or however you want to do the large distance scales, seems ad hoc. Okay, so as usual, this sort of claim is based on intuitions, but here's what I'm going to appeal to bolster my intuitions. Again, a reminder that what I'm trying to do here is to proceed with the interpretive project for quantum field theory. Right? So, pretending that quantum field theory gives us a true description of the world, and then I'm asking what sort of world quantum field theory describes. So it's not legitimate to say, to appeal to some form of quantum gravity, and then come in and say, well, if that variant of quantum gravity is true, then space is discrete anyway, so we might as well put in cutoffs into our quantum field theory, because that's not the project that I'm pursuing right now. Okay, so the question that we're interested in now is it physically well motivated to introduce cutoffs into quantum field theory in order to solve this problem? And I think the answer seems to be no. And one, if we're talking sociology, one sort of sociological indication that this is true is I don't think that anybody takes quantum field theory to have demonstrated to us that space is discrete or that the universe is finite in spatial extent. Right? In contrast, much different arguments are appealed to in quantum gravity, in cosmology. There's some experimental considerations as well as theoretical considerations in quantum gravity for introducing the assumptions that space is discrete or that space is compactified or are spatially funded or something like that. Okay, so contrast this case with that kind of case. In the quantum gravity case, in particular cases, or in cosmology, we have physically well motivated grounds on which to wonder whether space is discrete and spatially finite or not. In contrast, I don't think we have those sorts of grounds. Okay, so now I get to the point of dealing with objections. Did I start with that?
We started about 5 minutes late, so we have
Great. So, right. So here are the objections. Two of them, I guess, are not that surprising because I started out saying that I would remove these limitations. Okay. So, of course, space-time actually has 4 dimensions and not 2, 3, that. Or more. Second of all, the year is actually 2009, not 1970. And third of all, even though I think in this talk, David talked to points as if he wasn't going to be pushing this line, I want to dispel any notion that there is nothing to be gained from pursuing the axiomatic protocol. All right. So first of all, what do I think about this complaint that space-time actually has 4 dimensions? And so far, we, the mathematicians, have not been successful in constructing a model for any interacting system in 4 space-time dimensions. Okay, well, the first thing to say about that is a simple thing, that it's a hard mathematical problem, so maybe that's not too surprising. But here's the more substantial one. I think it's important, and here's where it's important to think about what I've been calling the formal QFT project, as opposed to algebraic quantum field theory specifically. So if we regard the formal QFT project as being a project which on the one hand is trying to figure out what the physically reasonable set of principles is for quantum field theory, figuring out how to axiomatize the theory, and then in conjunction with that, trying to construct rigorous models for interacting systems, hopefully realistic ones, then I think that this should be regarded as a program which has yet to be completed. So obviously it hasn't been completed yet because we don't have the sort of realistic model that we want. But I mean something even stronger than that. So what if some brilliant mathematician comes up with some sort of no-go theorem, which establishes that it's not possible to construct a rigorous model for any interacting system of interest in four dimensions in the algebraic framework? Well, I'm not saying I think that such a thing is likely, but it's possible, right? What happens if we get such a result? Well, I still don't think that that we should think of it as being game over for what I'm calling informal variant of quantum field theory. Then I think the next step would be to look back at the principles, the axioms of algebraic quantum field theory, and think, gee, are there ways in which we could tweak these axioms and still come up with something that we would regard as being a unification of special relativity and quantum theory? Okay, so what one is doing in that light actually gets to be quite a difficult project to show that it's not possible to construct models. So one of the things that I'm trying to stress here is that as philosophers of physics, we should be sensitive to the historical context here. We should be thinking about quantum field theory, I think, as a theory which is still in the process of being formulated. Maybe we have it with the algebraic formulation, I don't know. But we should think of quantum field theory as a theory which is in the process of being formulated. So by analogy, of course, there are other cases in the history of science where we think that the first guess of the physicists about the content of the physical theory, about the best way to formulate a physical theory, turned out not to be what nowadays we think is the best way to formulate a physical theory. So think back to Newton's Principia. Think back to the way in which Newtonian mechanics was presented in Newton's Principia. Much different from the way in which we find classical mechanics presented in modern textbooks. It took a couple hundred years to get from the point of Newton's Principia to get to the point where we see the water formulation of classical mechanics. So I think something similar might be happening here. The physicists who won the Nobel Prizes made a pretty good guess about what the content of quantum field theory is by introducing a set of physically reasonable principles. But I don't think they got it quite right. I think what the axiomatic program is about, formal QFT is about, is starting from that point and then trying to figure out how exactly to formulate the physical content of the theory, how precisely to formulate the axioms of the theory. All right, so here's a quote from Hagg, which I think is sympathetic to the viewpoint that I'm trying to push. So here he's explaining why he likes this term, which was first introduced by Yoss in 1965, of general field theory instead of axiomatic field theory. He says the word axiom suggests something fixed, unchangeable. This is certainly not intended here. Indeed, some of the assumptions are rather technical and should be replaced by more natural ones, as deeper insight is gained. We are concerned with a developing area of physics, which is far from closed and should keep an open mind to modifications of the assumptions, additional structural principles, as well as information singling out a specific theory with a projective frame. Of course, he's saying this in the context of presenting algebraic field theory. Okay. Here's an objection to the objection, objection to the response to the objection. Okay, so I've just told you that we should be sensitive to the historical context, maybe we haven't gotten there yet. But wait, if I'm a philosopher of physics and I want to pursue this interpretive project of interpreting quantum field theory, how does that help me if I don't know that we have the right theory yet? Should I just give up and go back to classical mechanics, which maybe we do have right now, and try and figure out what's going on with classical mechanics? No, I think actually what I said is more helpful than that. So first of all, I do take the point that interpretations of quantum field theory based on extant axiomatizations, for example, the algebraic formulation, should be regarded as provisional because for all we know they can change. However, having said that, we have to remember where the axiomatic program started. The axiomatic program started by looking at Hagg's theorem, by looking at this set of physical principles embodied in the cutoff variant of field theory, embodied in the standard textbook approach, and they started by refining that set of principles. Okay, so what does this mean? It means that there have already been a number of iterations of this process, so we've already had a number of refinements to that initial starting point of that set of principles. So what does this tell us? Well, it tells us that the best we can do at the moment is to look to the algebraic formulation or some other plausible formulation of theory in order to interpret it. Okay, so certainly what we should not be doing is writing off all the progress that's been made in solving these in addressing these foundational issues, in sorting out what the physical principles of the theory really are. The best thing we can do is look at formula, look at axiomatizations like the algebraic axiomatization. Okay, so we're still better off looking at formal quantum field theory. All right, so the year is not actually 2009. The year is actually 2009. It's not 1970. So I haven't said anything about modern developments. So one thing that happened after 1970 was, of course, the development of renormalization grid methods. I'm running out of time, but I'm just going to say briefly that actually, I think, as far as I can tell, renormalization grid methods actually reinforce some of the points that they're making here. Maybe surprised. Renormalization grid methods actually reinforce some of the points that they're making here, because what we learn by applying renormalization grid methods is that empirically, on an empirical level, quantum field theory is insensitive to what's happening at small distance scales, right? So empirically, as far as we're able to test the theory, we find that we're not able to learn very much about what's happening at small distance scales. So I think that this just reinforces my underdetermination point, right? That if this is the case, if there are structural limitations within the theory, if there are limitations about the sorts of things we can discover empirically, maybe it's not so surprising we find this situation where we have a number of different variants of the theory which are all compatible with the empirical results that we have available to us. All right. The other thing that happened, of course, was QCD and the standard model. So what I'm thinking of here is actually a particular objection to the way I set things up. One of the reasons that the axiomatic program was pursued more vigorously in the 1950s and the 1960s was that it seemed that we were not going to be, that physicists were not going to be able to get a theory which was able to deal with strong interaction by standard perturbative methods. Right? So it seemed like the axiomatic program might be the way to go in order to make progress on those sorts of problems. Turned out there were other solutions to those kinds of problems. But I hope that it's clear from what I've said already that there's still independent interest to the program. Still, those were sort of contingent sociological factors which drove physicists to work on it. But I think that there are a lot of other reasons now to take the program seriously. All right, objection number 3. There's nothing to be gained from pursuing the axiomatic program for quantum field theory. There's nothing to be gained from this program which I've set out. I'm trying to figure out what the theoretical principles of quantum field theory are. Here's where I start talking about the real world rather than my counterfactual interpretive project of asking if quantum field theory is true, what the world is true. Okay, so quantum field theory is not going to be our quantum theory. Even I admit that. Okay? It's not our quantum theory. Our ultimate goal is going to be a theory which can handle gravity as well. Okay, so given that aim, why should we be so interested in pursuing quantum field theory to its final conclusions? Shouldn't physicists, all the people, the mathematicians, the very smart mathematicians who are working on this very hard problem of trying to construct models for four-dimensional interactive systems, shouldn't they devote their energies to pursuing some form of quantum gravity or string theory or whatever? Okay, well here's what I say to that kind of objection. My first response is, it's worth pursuing this program to its conclusion because there's an interest, as a philosopher of physics, because there's an interesting, very important foundational question here, which people may have taken have been solved already, but I think one of the interesting ways of, interesting results of thinking about these variants of quantum field theory is that we see that maybe this issue is not as settled as we would have thought it was. So there's still a question, I think, of whether quantum theory and special relativity are compatible, which is going to be a matter of whether it's possible to come up with some axiomatization of the theory, some set of principles of the theory, which we recognize as being, some of which are both artificial relativistic and some of which are quantum, and which have models for realistic systems. Okay. The second point I want to make in response to this objection is that I think that there's the potential that new physics in the domain of quantum field theory could shed light on quantum gravity. And I should stress that I think that I've made a lot of other arguments which don't hinge on this controversial point. I'm not, and this is a pretty weak point. That as a matter of heuristics, as a matter of thinking about how we can get to quantum gravity, it seems at least reasonable to think that pursuing these programs is going to be useful. So there I have some examples. The latter set of examples are interesting not only for the light that they might shed on those issues, but also for the thought that that loosening up the axiomatic, the mathematical structure of the theory might actually help in solving this problem of finding realistic models in four dimensions. Okay, so in conclusion then, here's a quote from Streeter and Whiteman, 1964. The main problem of quantum field theory turned out to be to kill it or to cure it. Either to show that the idealizations involved in the fundamental notions of the theory, relativistic invariance, quantum mechanics, local field, etc., are incompatible in some physical sense, or to recast the theory in such a form that provides practical language for the description of elementary particle mechanics. So their choice of the term practical language might strike some as a bit strange, but I think that the spirit of what they're pointing out here is in the same spirit of what I've been trying to urge. That as philosophers of physics, we should be most interested in axiomatic variants of the theory, in particular the algebraic formulation of the theory, because there's an important matter of physics to be settled here about what the theoretical principles of quantum field theory are, viewed as the theory which best unifies the special theory of relativity and quantum theory. And furthermore, there are also those issues having to do with how to interpret the theory. Different variants of the theory are going to come in different interpretations, so there's those sorts of issues, as well as the conceptual bases.
Hagg says, and I think you're approving of this, we should keep an open mind to modifications of the assumptions. Okay, so I kind of found that quite second. In that case, here's a proposal to modification of the assumptions. Short distance cutoffs. And why is that?
Right. So why wouldn't I accept short distance cutoffs as a proposal for? And actually, I think that's what I was doing when I was launching my earlier argument, arguing that that sort of proposal seems to be ad hoc. And actually, I'm much. Okay, we'll talk about your talk too, but so it seems to me to be ad hoc because of the way I set up the problem, right? So the way I set up the problem is we start out with physicists' first attempts at trying to formulate quantum field theory, which involves postulating a physically reasonable set of assumptions, which then turn out to be inconsistent for cases that we care about. So how are we going to respond to that sort of problem? Well, if you're going to respond to that sort of problem by introducing cutoffs, then I think that you're going to need it's a physical question, right? What are the correct set of physical principles for the theory? Then you're going to need some physical motivation for however you're going to interpret those cutoffs. So you can interpret the cutoffs as being space is discrete and finite in spatial extent. then I think you're going to need some better reason than just the fact that the first set of things you came up with, right, as being plausible principles of quantum field theory turn out to be inconsistent.
Well, okay, so
You need some further physical motivation.
I mean, try to see if we agree on the specific potential use of the clearing point. I mean, so first concession, as I said before, would be, I think it's consistent to take a different line to IR using divergence.
Yeah, okay, so, and I wasn't talking about the IR case.
Well, I was thinking the infinite of the longest is pattern. So I took that in mind.
So, well, okay, so the way I set things up, I was talking about the longest is cut off. But I tried in the latter part to focus on the
So I think actually within the two-dimensional universe, and the actual best QFT we had was had only longest divergences. Then I agree with you. The locus constraint is going to be in other cases, and I think it's going to partly be driven from whether it's really fair to call that an ad hoc route in the light. Let me not
right, yeah, which is why I was going to start getting
so
into
leave that for the day.
Right.
That's just to ask one more thing about the framework of your opinion.
Actually, let me comment one thing on that. I should say that I take it that what would be great is if we had a whole series of Hagg theorems. Right? So Hagg's theorem is just this very simplest case of, and even any interactive system. But I think it would be great if we had a second order Hagg's theorem, which would apply to theories which have which need UV cutoffs in addition to the IR cutoffs. So I think that I take it that the story I'm telling there about the source of the renormalization turns equal for the other cutoffs as well.
I mean, that's just kind of I mean, so your part of the idea out was the interactive project I'm going to engage on is to interpret this kind of theory conceived as to when, of course, that's fine as a project. Now, and I'm thinking of there are other interactive projects, one could do take an interactive project of plastic mechanics, one could take an interactive project of geometry, an interactive project on QFT, which is category, and the latter project is what I and then, I mean...
So are you objecting to the counterfactual part? No, the way I set up the definition of
there's no objections to that. I guess the only thing I think is that the last of those various interpretation projects, the interpretation project of interpreting QFT assurances cutoffs, one of the various reasons one might want to carry out that project is your project to pay for the investigate. But you seem to want, I think I'm still not quite clear on why you think that, notwithstanding the fact that this is an empirical theory based on historical evidence, you don't think the interpretive project work that it says is a useful enterprise.
Okay, so you're wondering about how I'm getting from the case of two spatial dimensions to two spatial dimensions to the more
yeah, I mean, there's a very quick essentially society. I'd say that the very fast argument to say don't bother doing that interpretive project in two dimensions is entirely tied into the existence of lambda 5 4 sub 2. And I think I completely want to concede to you that if we had Yang Mills in 4 dimensions, then that would be a very good reason not to do that project. But of course we're not in that situation. So I'm still not quite sure why this project can be carried out given where we are.
So right. So where we are is we even in that single case we can see that something's gone wrong with the way that quantum field theory is done in standard introductory textbooks. The thing that's gone wrong with the way quantum field theory is done in standard introductory textbooks is a set of physically reasonable assumptions are introduced, and it turns out that given that we're interested in, as you agree, we're interested in representing interactive systems, we can't accept that set of physical principles for the theory. Okay, so the question is, then what do we do next? I think what we need to do is refine the principles, right? Because this is another point, right? As a philosopher of physics, what I care about is when I'm engaging in these conceptual projects, when I'm engaging in these interpretive projects, my starting point is what the theoretical principles of the theory are. Okay, so it's not overly interesting to me to think about, I think the empirical confirmation of theory is important, but in order to have something to work with, I need to know what the theoretical principles of the theory are. And so that's what I'm interested in more so than the empirical confirmation. Especially given that I think that the empirical confirmation for the theory is quite distant from the theoretical principles.
why don't I start there?
Okay, yes, by all means, find principles to reconstruct, but we're 39 years on from 1970. People of incredible industry and brilliance in mathematics have been working at this for all this time, and we have made, from a certain perspective, so little progress, not a single example of an interacting quantum field theory before he mentions it. When does one start to think we're on the wrong track? Because, look, you had the analogy with Newton.
Right.
I want to offer another analogy, because in the Newton case, yes, it was 100 years, let us say, before we got our current formulation of classical mechanics, but every time there was a development in mathematics that was relevant to classical mechanics, the application was quick, the results came out fast and furious, and so there was steady progress. It seems to me the better analogy is with late 19th century, when the Cambridge mathematicians were dismissing the innovative manipulations of Oliver Heaviside, who was differentiating discontinuous functions and integrating their derivatives, manipulating infinities in non-rational ways from the point of view of the mathematicians, and they dismissed what he was doing as meaningless. Now, eventually, people found the Laplace transform method of making sense of what Heaviside was doing, but they wouldn't admit his impulse function, what we call the Dirac delta function. They wouldn't admit that as meaningful. That had to wait for the development of generalized function theory and distribution theory, post-war 20th century mathematics. So what I'm suggesting is that it seems to me a sea change is needed in attempting to formulate a rigorous approach to Lagrangian quantum field theory. That in some sense, and I'm not trying to suggest that I have a clue as to what this sea change would consist of, but I wonder, you know, if physicists eventually abandon Lagrangian quantum field theory because maybe loop quantum gravity finally becomes a viable theory, or even superstring theory becomes a viable theory, what then? Do you still continue pursuing either the physicists' QFT or the philosophers' interpretation of QFT?
Right, okay, so I disagree on a number of points with the way you tell the story naturally. So one thing I would point out is, sure, brilliant mathematicians have been working on this project, but look, what's been happening in physics in the last 40 years? Well, everybody sees that the big project out there, right, is the quantum gravity project. So it seems to me that actually that might have played some role in why further progress hasn't been made. That a lot of the best people who are interested in winning the Nobel Prizes, the people who are interested in pursuing physics, see that there's there's the dream of the final theory out there, right? So that I think that actually that factor, that sociological factor, has been attracting people away from working on this kind of project, right? Which is the sort of project which is really important for people who care about, for philosophers of physics. It's an important project for people who care about the foundations of the theory. It might also be, I hope it's also going to be an important project for quantum gravity, but it's really hard, right? It looks like if you're interested in making progress in your lifetime on quantum gravity, then you might look at different ways of going, because it's hard. So I don't see anything wrong with that. As far as as talking about drawing the historical parallels goes, I mean, I don't really see a problem if science works slowly sometimes. I don't really see a problem if it takes hundreds of years to figure out. There's lots of examples in the history of science where it took a long time. Poor Copernicus, you don't see it. It takes a long time to get right. That's right.
David, do you want to ask?
Just a very quick observation. I mean, who knows what sociology is? I mean, the obvious alternative that occurs to me if you want to say why we're working on this is an awful lot of people just felt to be solved to their satisfaction afterwards.
Sorry, it's been
There's an awful lot
solved.
of people in physics, in theory of physics, I think, thought afterwards and the problem is solved to their satisfaction.
Right, but of course it's not a physicist's problem, right? So it's
Bob?
So the debate really isn't about So, I mean, it seems to me there are explanatory reasons for introducing cutoffs, because that enables us to provide certain kinds of explanations, be it without having to sort of interpret it, that is, find the fact that space-time is discontinuous or discrete in some sense, right? We can introduce these, and in fact we introduce them all the time for explanatory purposes. That is in part the point of the normalization group. It's nice that in that case sometimes there actually is a lattice constant or something in PL2, right? The other thing is, it seems to me that there's another way of looking at the history, right, to support the kind of cutoff approach, and that is, in very many situations in trying to understand the relationship between the various phenomena that we see, we have to appeal to separation of scales, right? So even in the case of continuum mechanics versus some sort of underlying discrete classical mechanics or hydrodynamics or molecular dynamics, we tell various stories about those relationships by appealing to some separation of scale, which is equivalent in a certain sense to imposing a kind of cutoff for looking at these things in various different asymptotic limits, right? So there's a kind of whole history prior to even the development of the official renormalization group that appeals that applied mathematicians have been using for a long time to try to explain what's going on in the macro world, even views about this kind of stuff.
Right, okay, good. So, what the first question about whether there might be certain explanatory projects for which the cutoff variant or something like that is going to do a better job than some sort of axiomatic variant. Yeah, that's an interesting suggestion. I'm not sure. I guess I'd have to think more about particular cases and particular sort of explanation. As far as the point about scales goes, I don't want to suggest that there's nothing to be learned from renormalization group methods or something like that. But my point is just that I don't think that by thinking about renormalization group methods, you're going to get away from this fact that if you care about physical principles and theory, then you're going to have to engage in this axiomatic project, if you're interested in formula.
In the sense that for it to be physically well motivated is to point to something in the world as opposed to pointing to the sort of mathematical power that we gain in providing explanations and which is another thing that we as physicists should be interested in promoting.
Right.
So, I think you and David agree in the sense of seeing these approaches as being important and distinctive rivals in various ways. And in your case, it wasn't clear to me whether, when you say that the two approaches disagree on the physical content, it seems that as far as we know, they disagree on the physical content in the sense that they modify different principles. But it's not actually clear until we have something that we can directly compare, namely the interactive theory in 4 dimensions, that we can really clearly state that they disagree with us. I mean, maybe you could say for the 2-dimensional approach, you can clearly say how the cutoff approach differs from the formal variant and justify the thing that they disagree with the content. But it seems like it's more of an initial starting point. They clearly disagree. But at this stage, it's maybe still possible that even they start off with a formal approach, that you end up with something that could be reconciled.
Okay, good. So a couple things there. I mean, so I take it, so you're wondering if in this process of refining the axioms, if you could come back to your starting point and figure if you're going to decide, well, it's one thing you eventually decide is that you're going to introduce cutoffs, right?
Well, or that you end up with something that looks formally similar enough to what you were doing. I mean, perhaps in some domain you say that it's equivalent to what you're doing with the cutoff, but for another one it's form. I mean, then you have a difference in physical content, or you might end up with something that's actually fairly close structurally.
Okay, so So the way I'm thinking about this case, these questions about the physical content of the theory have to do with a set of principles of the theory. So they're divorced a little bit from the further questions about whether we're going to build models of certain interactions in four dimensions. So they're divorced a little bit from the empirical considerations, which is, as I said, why I think this is an interesting case of underdetermination. So forgetting about those questions about model construction or whatever, well, forgetting about the questions about empirical tests and models or whatever, I think that there's a sort of progression, right? The problems get harder as you start dealing with more and more complicated interactions. So I take it that it seems like a reasonable conjecture that the first little changes that you have to make, what you're going to have to do is you're going to have to make bigger and bigger changes, right, as you go along. So it's not like you're getting it up when you're starting to get it. And Hagg started telling us you can, so it's like that. A second thing to note, which is kind of interesting, is that if you look at these models that have been constructed, the rigorous models, there's a little bit of circularity involved. So what you want to do is you want to find a model for a particular interaction. How do you determine that this particular Hilbert space that you found with, you found a Hermitian Hamiltonian, you found Doreen, which is all and all that? How do you determine that that's representing some particular interactive system? Well, then you kind of go back to the Lagrangian approach, right? And you check the S matrix elements against the Lagrangian approach, which is actually perfect because, from my point of view, because it means that because of this little bit of circularity, I don't really have the worry that we're going to find some model eventually, and then we're going to then the predictions we get are going to be different from the predictions of Lagrangian quantum field theory. I don't think that's going to happen. The question is whether there's a model out there that makes sense.
Okay, it's kind of coming back on this issue of how models can come up with that. I'm following the logic of the argument, that's something very, very important logic. So, advanced logic, I'm going to ask a very unfair question that I'm asking to make a rhetorical point about this, I expect an answer. And the unfair question is, why is there no full thermal interaction cell? Right, okay, the reason I'm asking that is that I can give you an answer to that question. Based on normalization methods, based on the assumption that the physics inside the model is cut off in the scale very large that, and because the bifold contract is more normalizable, the coupling, because we have strongly get the coupling costs absolutely speaking at 1.2 to be very, very small compared to the physics levels. And that kind of explanatory story is doable in the standard model in color quantum field theory. It seems those are the kind of things that seem to suggest to me that the situation is important different from 1942.
Okay, so again, I take it that because the project is a really general project, right? It's a really general project of trying to figure out what kind of structure, what kind of physical content, any theory which unifies special theory relativity and quantum theory would have, right? So I don't see any reason why the standard model should be one of those theories. So if what we care about, so again, if you agree with me that the physical principles of the theory are central for determining, or a central part of the theory for determining.
But the dialectic, if I got it right, basically goes that these are perfectly well formulated alternative things to look at, satisfactory and you're making basically having two prongs to the argument you're making. One is to say that here's the positive case for not giving up on the foundation work now to record. And secondly, here's the negative case for not doing foundation work in cut-off. And as far as I can see, the bulk of that negative case, the resting case, that the introduction of cut-off is basically just an ad hoc move. Now, my fourth example is my fourth element is just supposed to be an example of a move that one can make in the standard model with cut-off, and where the foundational principle that's playing a role there is precisely the cut-off. So I'm really struggling to see why. I mean, I can pick some examples, but why
Right.
it's fair to say it's ad hoc in that situation. But clearly, hypothetically see that in a situation where the only thing it's doing is fixing a problem, and then we charge about what it's doing pretty good, particularly with this alternative fix, doesn't do it. But that just seems so far from the situation we're in, given the kind of arguments that I formed in our
Right, well, okay, but then I'm still gonna, I don't see how that sort of, those sorts of grounds are going to be grounds for then accepting that set of theoretical principles. How those sorts of explanatory moves are going to be relevant, right? Because again, right, that it's the fact that, well, so we haven't gotten there yet for this.
Yeah, but this isn't a criticism of the positive case for QFT. It's not directed. It's meant to be negative.
Oh, okay. So I don't care if physicists do it. I mean, I'm interested in
say.
Right. I mean,
I'm not philosophy physics. I'm talking about why philosophy physics
right. Why philosophers of physics
should not accept your reasons against doing foundation work with QFT.
Right. Okay. So why I think you're doing the wrong thing?
Yeah.
That's too much time.
Well, that'd be great.
Right. Okay. So, because precisely I think that as philosophers of physics, if we're trying to sort out what the theory is about, if we're trying to sort out conceptual issues, if we're trying to sort out foundational issues, if we're trying to sort out these empirical issues, then we should be thinking about what the principles of the theory are. Right? But look, so then what are the principles of the theory and how do we determine it? Well, I think that the way we should determine what the principles of theory are is thinking seriously about, in this special case, it's the special theory of relativity and quantum theory as being a unification project, right? So what I care about is how exactly we're going to get a set of theoretical principles which combine elements of special relativity with quantum theory.
I've offered you a theoretical principle, which is that the physics of the universe, the physics of quantum field theory is kind of short examples. And you're saying you don't think that physical principle has been taken. In the case for it, it seems to be on top. And my line is that, seems to be that it is on top.
Right.
And my line is basically to say something like, here I have a principle which I've introduced to solve a certain problem in my framework. That thing I've introduced makes a different novel prediction in a domain set from the code I've introduced. That prediction is empirically rubbish. I can't think of if that kind of thing doesn't count as central power as evidence for some principle in
But
science.
we know a priori that if you're going to go that route, if you're going to go the route of if you want a well-defined, consistent Lagrangian quantum field theory, we know a priori you're going to have to introduce cutoffs. Right? Are you telling me anything different than that? Right?
No, I'm telling you the introduction of cutoffs produces novel predictions that weren't these cutoffs built in and a problem.
I'm not sure about that.
Well, the fact that there's no significant scale Hawk-Bell interaction center.
I don't know. I think that you're coming back to this problem that if you're going to want to draw conclusions from starting from that framework, if you're going to want to draw those, if you're going to want to draw inferences, if you're going to want to make arguments, you're going to be forced to introduce cutoffs.
I've got a couple more questions for you. Maybe we can continue this dialogue in the panel discussion. No? Alan?
So I'm curious, what are the prospects for positive movement programming if we are still in this co-8 state? Like,
You mean by
or some-
positive movement?
can you report some interpretation in the philosophy of physics, any interpretation of axiomatic quantum field theory? Like what can be done or what has been done that you think should be like reported?
I think we've heard a lot of talks this weekend that answer that question.
That's different.
To me, there's a difference between discussing whether an algebraic axiomatic quantum field theory is a viable program in mathematical physics and deserves to command the attention of a generation of important physicists and mathematicians, and arguing for its importance for philosophers of physics who are interested in specific foundational issues, even if one were agnostic about the first, and I probably am. It might be the arena in which one can sharply pose certain questions which would be difficult to pose otherwise. So if we're going to have an argument that goes on and on and on about whether quantum field theory is local or non-local, sense is in which it was and was not. And it seems to me whatever else is the case, this algebraic framework does lend itself for discussing a lot of the issues which traditionally have interested philosophers.
Yeah, if I could respond to that, very sympathetic to the thrust of your suggestion, but the limitations of what have been achieved thus far within the program mean that the kind of questions that you can ask in a very refined way are exceedingly limited because you don't have any examples of models in this program that are describing interactions in four-dimensional space-time. So you can only pose questions that can be answered one way or another for free fields.
Wait, I take it the point of my talk was that that's not true. I mean, it is true that we don't have any models, but I take it that one of my points was we've made some progress, right? We've been able to refine the set of assumptions we started out with, right? So,
we can certainly settle conditional questions. If there were theories that satisfied these axioms, what could one say about them? And could one, within this framework, make certain, perhaps, interesting distinctions?
Yeah, but it's entirely possible that that's going to end up being an empty question because there may not be any such theories within that framework. Forget about the fact that we don't know them. There may not be any.
Well, I mean, it seems to me that's, let me just say one last thing. I mean, there are mathematicians who spend their lives thinking about what the implications would be concerning large cardinals and so forth.
And as a mathematics program, I have no problem with it at all.
But it also can be illuminating about the structure. It can lead to a certain kind of understanding. Any?
Yeah, so, I mean, you said that this program of axiomatic quantum field theory is basically not supposed to include gravity. That gravity is supposed to be something different because we have to quantize general relativity. So if the scale at which this becomes important is the Planck scale, say, and what you're saying is that you think things look like flat space-time, quantum field theories on scales below the Planck scale, and adding above the Planck scale, they look like something completely different, then why isn't that a cutoff in the sense of the previous talk?
so a cutoff in the sense that we don't think that quantum field theory is going to describe what's happening in the real world at
Sufficiently small scales.
sufficiently small distance scales.
Yeah.
Well, presumably that's true, right? But I don't think that that's the point at issue, right? So, that's kind of why I was careful at the beginning to set up the question of quantum field theory on its own grounds, right? Without mixing in considerations having to do with quantum gravity, and then so to think about what quantum field theory says about the world in the absence of quantum gravity. But then later on, I think just as a point about one possible way in which we could go about trying to figure out what our theory of quantum gravity is, we could start, as John was talking about this morning, we could start from quantum field theory and then try to work out from there, right? So I think that there's still value in this project of trying to see quantum field theory in its own terms and trying to figure out whether it's quantum field theory that tells us that it breaks down, right? So there's still this question about whether it does really break on its own terms, because quantum gravity aside, break down to small distance scales, whether it tells us on its own terms, quantum gravity aside, that space is discrete, space is finite, whatever, right?
But gravity is a universal force. You can't, really say.
Yeah, and that's why I think
I mean, you can in a certain approximation, but as a sort of fundamental question of what are things really like, you can't say, oh well, let's just forget about gravity.
So it's something else to say, I guess. You're right. So I'm talking about a possible world in which quantum field theory is true, which is not the actual world. So I'm thinking about quantum field theory in those counterfactual terms. But I think something else to say about that is that that's the sort of project which I take to be interesting to philosophers, right? We're trying to figure out, to what extent does quantum field theory tell us about the real world? If we assume that quantum field theory is the whole story, how exactly is that approximating what we see in the real world? I think that's one interesting question you get asked.
Yeah, I think one thing that should be said in response to that question too is the principal difference between working with a cutoff and saying I'm not working with a cutoff, but I'm also not taking the theory seriously at short distance scales. I mean, it's the same thing that we do when we use Newtonian mechanics now, right? We don't cut off velocities at 3 times 10 to the 8 meters per second. We just leave those solutions there in the theory, and it's important to some things that we do that those solutions are there, but we don't believe the theory about the states it has that contain velocities, relative velocities higher than the speed of light. So similarly, Doreen's point of view would go along with saying, look, we have models of quantum field theory that say things about the scale below, the Planck scale or something like that. It's just we don't believe them about that. And there might be formal advantages to that, just like there are formal advantages to doing Newtonian theory, leaving in the fast-moving solutions and to doing general relativity, just like we do it without a length cutoff, right?
But the problem is that in quantum perturbation theory, at sufficiently high order, one has to sum over all possible intermediate states of arbitrarily high momentum and arbitrarily short length scale. And that's a feature that you don't really particularly have in Newtonian gravity. And so one always has to ask the question, well, what does one do with these intermediate states at these really high scales? And so one can't just say, oh, I'm only worried about what's happening at the particular length scale I'm measuring, and so I ignore all this higher stuff. In the intermediate states, I have to do the sum,
right.
And
So,
I have to ask in that sum, how do I treat these things?
Yeah. So that's an argument to the effect that you can't have a good theory without cutoffs. What I was saying was, here's the difference between a good theory without cutoffs and a good theory that doesn't have cutoffs, but that we don't believe about the short distance scales, which was, as I gathered, that was sort of the initial question, right? Was what's the principal difference between what Doreen is wanting to do and just applying cutoffs?
Well, my initial question was just that, by saying that, gravity has to be quantized differently, that's sort of an admission that nature imposes an actual cutoff scale.
Yeah.
And in the sort of weak sense of the beginning of David's talk, that there's some scale in which things behave very differently from the way they behave now, and we're not sure what that is. And so why isn't that tantamount to admitting the existence of a cutoff in the weak sense introduced at the beginning of this talk? That's really all I was asking.
Well, let's take a break and continue the discussion in the panel discussion. Let's thank